So in the previous session, we were discussing about mobility, right? Mobility of carriers. And we have seen that the dependence of mobility on temperature, right, with temperature basically. And we have seen there are two types of scattering, lattice scattering and impurity scattering. And we have seen their effect, I mean, one on the other, right? So one compete to the other, and at a particular temperature, we get a maximum mobility or maximum conductivity, right, for a given semiconductor. Now, uh, now when you bias a semiconductor, right? So we are discussing about all drift phenomenon so far. So when you bias a semiconductor or when you apply electric field across it, so what happens to the carriers, right? So first we'll just draw the um, its EK diagram, and then we'll see that how does it vary, or the conduction level, conduction band, valence band, this energy, how do they vary, and then from there we'll derive the drift current quantitatively. Okay, so if you consider an N-type semiconductor, so for N-type semiconductor, the majority carriers is electron, we all know by now, right? So let me just draw a N-type semiconductor here. Oops. Okay, so here we have a N-type semiconductor, and at thermal equilibrium, if we want to draw its band structure or EK diagram, so we'll just draw it off here. Change. Okay. So here we have the conduction band. Then let's say this is the valence band. So this is EC, conduction band energy, and here we have EV. Now we are talking about without any biasing at thermal equilibrium, right? So generally we draw it like this. So this side is also grounded and the other side is also grounded. And so how do you ground it? So basically we put, contacts here. Contacts in the sense, most of the time we put thin metal layers on both of the sides, right? So these, here we have basically metal semiconductor contacts. And we assume that these are ohmic contacts, okay? These are in ohmic nature. Later we will study that metal semiconductor contacts can be two types. One is this ohmic and the other one is rectifying, or kind of Schottky junction. So we'll see that different condition, at what condition it becomes ohmic or what condition it become rectifying in nature. We'll discuss later on, but for time being we'll consider this metal semiconductor, this junction is ohmic. Okay, so in this situation, uh, if the semiconductor is intrinsic, then the intrinsic energy level, now this intrinsic energy level, it will be exactly in the middle, right? We have seen that also. And if you're considering this semiconductor as N-type, so for N-type semiconductor, the Fermi level is near the conduction band. Okay, if I take a different color, it will be better. So it's somewhere here. We're just assuming, okay? So again, it depends on, doping concentration, right? This position, that how far from EC, this gap depends on our doping concentration, right? So we learned this. Now when you bias this semiconductor, in that situation, what happens to the band diagram? So let's draw another, or we can, okay, let's do it on the side only, better. So the same semiconductor, now we are biasing it. right? So this side is, let's say, grounded, and other side we are applying a positive potential of V, and this is an N-type semiconductor. So what will happen? The excess, or sorry, the majority carriers electrons, they'll move towards this positive electrode, and the holes present in this semiconductor, they will move towards the ground, right? Or if you write down the electric field, so electric field is in this direction. Electric field is positive to negative, sorry. So electric field direction is in this direction, right? Positive to negative. So this side is positive, comparatively this side is negative. So field direction is positive to negative, and electron moves away from or opposite to electric field. So this is fine. All right, now if you draw this same, try to draw the EK diagram. So in this diagram, you can see that the x-axis is basically the length wise, right? We are drawing the lengthwise of the semiconductor, not like exact EK. We draw like momentum versus energy, but here we are drawing physically. Like the x-axis, we have the length of the semiconductor. So we can start from, let's say, x equal to 0 to x equals to L, right? So this EK diagram is like that. And in the y-axis, we have potential energy, or simply you say energy. So same case here. Now, when you bias, so what happens is the conduction band. So this side, let's say this is EC on the left. So this side is grounded. So the potential energy, it was V equals to 0. And here also potential energy in this position at this thermal equilibrium condition, it was 0. But in this side now potential energy is higher, right? We have applied a positive V. So what happens is this side, the conduction edge, conduction band edge, it will be lowered, right? Potential energy will be lowered for this electron, and the electrons, I mean, at this side, right? So our EC, it will get bent like this. Need to just connect this. So this is now our the conduction band edge after the biasing. And same way you can draw the other energy levels, because they'll be just parallel to it. So let's draw the valence band first. This is the valence band, EV, and then comes EF, and then we have the intrinsic level. Here we have the EI and EF, right? Okay, so in this situation, or if you try to imagine that what happens when we apply a voltage here, so the electron present in the semiconductor material, the free electrons basically, so they try to move, right? And they try to acquire kinetic energy. Because of this electric field, they will experience a force, right? That is minus Q into E, right? This force they will experience, and the electron will start to move from this side to left to right side, right? So this is our electron movement. Now while moving, they will collide with different ion, lattice, or the impurity atoms. So again they will transfer this kinetic energy into vibration energy. So that's where the resistance or resistivity concept comes in. So it will transfer that kinetic energy, and so its total energy will reduce when it collide. Then again it will start gaining energy. Again it will collide, again it will start gaining energy, right? It will collide and the energy will go down, and like this way the electron keeps on moving and it reaches to the to this end of this semiconductor. And as we assume that these are ohmic contacts, so the electron can easily it will be collected at this electrode on the right side, and it will go via this battery. Generally it's a battery, right? So it will go through the battery, right? And same case for the holes happen. So so you can assume that holes are kind of bubbles under the water, right? So they tend to move upwards, and for electrons it's easy to move downwards. For holes, it is always easy to move upwards, because for holes the potential energy increases in this direction, right? And as it goes up for holes, the potential energy decreases, right? So what happens for the holes? So they also follow the similar pattern like electrons, keep moving, and then collision happens, and like this process goes on. And when they reach at this electrode near to this here, so here we can see this is a ground port, or it will recombine with some electrons present in this metal, because this whole concept is not there in metal, right? So to realize this, so it will recombine with one free electron present in this metal plate, and this circuit will complete. So this hole will recombine with this electron, and this electron basically it completes here. The same electron which goes, we can draw this way. Right, practical circuit is like this, right? So this is a negative pole. So this electron goes from this side and it waits here in this metal plate. And when some holes reaches to this metal plate, or this electrode, it recombines with these electrons, and this circuit completes, and this way the current continues, and the driving force comes from this battery, right? Okay. Yeah, so now let's try to understand the electrostatic potential energy here. Okay, so we'll define few parameters like this electric field. If we consider the length of this semiconductor is L, and we are applying a potential of V, so the electric field will be voltage by length, right? And again, depending on this potential, how you're applying, like which side is plus and minus, that will define this direction, right? So E equals to, in general we write just E equals to V by L. We don't write this vector because it doesn't look, one side is vector, other side looks like scalar, but it is not scalar, because this voltage, how the we are applying, right? It could be this side plus minus, or it could reverse, right? So it has a direction, and depending on that, this electric field will flip, right? Whether it is left to right or right to left. But in general, we best to remove write simply like this. So this was X. So electric field, the value is just voltage by length. So we're using small l. Something wrong. Something is wrong. Okay, this button got pressed here. Okay, now it should be fine. Yeah. So E equals to V by small l. Okay, now the electrons, as we know that electron will experience this force minus Q into E, right? The electrons present in this electric field, they will experience the force Q into E, and which is actually equal to the negative gradient of the potential energy of electron. So it's, you can write it like gradient of electrons potential energy. So gradient of potential energy, it's again unit is force, and left side is also force, right? So this, and gradient, how do you find gradient of potential energy? Now electrons potential energy we define as the energy of conduction band, right? Or the bandage, right? This EC, this is the potential energy of the free electron, right? So it's like minus DEC and gradient, so dx, right? So we can name this equation 1, and then okay, then we can just rewrite this equation like this, that electric field E equals to, so minus O1, okay, minus minus become plus dEc dx, and you can write it as because this is just a derivative, right? This parameter, this parameter is just derivative of or gradient, right? So you can write it as dEi dx, because this EC and EI, they are parallel, or EF, all are parallel to each other, so their derivative or gradient is same. So you can write this way, because EC is parallel to EI, right? And we are writing it in form of intrinsic energy level. It's easier because later on we will be using this EI a lot when we go for PN junction and all. So that's why we are moving towards this notation. Now the electrostatic potential also defined as I mean the negative gradient of electrostatic so let me define one more parameter, then it will be easier. Electrostatic potential energy. So this is psi, and the negative gradient of potential energy, that is d psi dx, will give us electric field, right? This is another definition of electric field. If you tell this equation as, okay, let's put this one as 2 and this is 3, and then if you compare this equation 2 and 3, so in the equation 2 we have E equals to 1 by Q di dx, and here just write it off similar way, so equals to minus d psi dx, right? So if you compare 2 and 3, you can get that psi equals to minus EI by Q, right? If you compare equation 2 and 3. So this is one important equation. So it's like we use a lot, right? This potential energy is nothing but electric field by charge. But the derivation comes from this comparing these two equations. And the psi and EI, psi is our electrostatic potential energy and the intrinsic energy level. They both decrease linearly with distance, right? You can see that electric field is constant. Psi and EI, they decrease linearly with distance from this curve. EI is linearly decreasing, and the psi, if you consider the potential energy of electron, so this is also decreasing linearly. And in this equation, if you put that, so you get the electric field is constant, right? The psi is decreasing linearly, so d psi dx will be constant. So that means the electric field is constant throughout the junction. So sorry, throughout the semiconductor. I'll just write it off if it's not clear. So this psi and EI, they decreases linearly with distance. So that means the electric field, or this electric field E, is constant constant within the semiconductor. And the value of E is equals to V by L, right? Now we know the value of electric field, potential energy, how do they vary, and how is the band diagram after biasing for a N-type semiconductor. So similar way you can calculate, or you can do it for P-type semiconductor, right? And you can draw the same similar EK diagram for P-type semiconductor, right? Now let's move on and see that what will be the current contribution from this movement of this charge, right? These electrons and holes, because of their movement. So what will be the current? And when you talk about the current generated because of this external electric field, this current is called drift current, right? So let's derive, or let's quantify the drift current. So okay. So here we are drawing a three-dimensional one to understand, the cross section. Okay, so here we have a rectangular semiconductor which is having a length of L. So in this, the length is L and the cross-sectional area, this area is A. Okay, and when we bias this, or when you connect it to a battery, so there will be flow of current, right? So this current, let's say it is IN, and the current is entering in this contact, and the same current will come out, right, from the semiconductor. Now for this, So how to quantify the total number or the current or current density? This is current. Now current density, if you write, so it's current density, we write it as Jn, right, which is In by the cross sectional area A. So how can you calculate the current? So as we have seen that carriers are moving right from one end to the other end. So in this situation, current direction is this. So the electrons are basically moving in this direction, right? And the holes, they are moving in this direction, right? For this diagram. Now to quantify this, we have to define few things. So how can you quantify this for just for the electron? So this is current density for electrons we are drawing, right? Jn, and for electrons. So we are first doing the calculation only for electrons. So the current will depend on few parameters, right? So first of all, that how fast these electrons are moving. So that is their drift velocity, right? Drift velocity. And then it will depend on, again, this drift velocity depends on the electric field. And one more parameter is the carrier density, right? So N will define, so this is electron density per unit volume, okay? Or when you call density, you don't write like this, you say number of electrons per unit volume, right? Number of electrons per unit volume. That's basically volume density of electron. So these two parameters we need to invoke or we need to consider, right? So now there will be some electrons which is having different velocities, right? Not all the electrons will move at same speed, right? So what you have to do is we have to basically sum of the electrons, and each electron is having charge minus q, right? So if you know that how many electrons are passing through this cross section, and then multiply with the charge, multiply with its charge, then we can get the current, right? Or we are doing per area, so current density we can get. So it will be like minus q into vi, where vi is the velocity of that electron, right? Now this vi will vary from 1 to n. Velocity of one electron, first electron, second electron, like this, right? And we have n number of electrons per unit volume. So we have to integrate from I to n, right? So this will give us minus q into n. If you sum up this, and we'll get Vn. So Vn is nothing but the drift velocity as we defined, right? So the average velocity of electron is nothing but drift velocity. But when you consider one electron, like here in this summation, they could be different. But when you sum off, then the average velocity of these electrons, we consider it as Vn, right? So the total current density will be minus q n Vn, right? Now we know again in this Vn, or drift velocity, is minus q into E, right? We derived this. Sorry.
Sir,
Yes.
sir, how n came sir in that expression?
Yes, I'll just come to that. So Vn is minus mu into E. Yeah, so how this n term comes? Because we are summing up one electron, right? So the first electron, so if you just write it like this, so it's like QV1 for one electron, then the next electron will be QV2, QV3, right? And then if you take this Q as common, then you will get V1 plus V2 plus V3 dot 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 Vn, right? And then it will be Q into average velocity, right, into N. So Vn basically average velocity, right? V1, V2, Vn by N. Is it clear now?
Yes, sir. Yes, sir.
Yeah. So yeah, now if you replace this Vn equals to minus Q into E, so you'll get Q mu or Qn mu n into E, right? So this is the current density for electron. Now similar way, if you do it for holes, so the current density for holes will be again charge is Q, but the hole density will be different, P, right? And hole mobility mu P into E. So I'm not writing P is hole density, mu P is mobility of holes, right? So total current, if you see the direction, like they will add up, right? The electrons moves this way, but the current contribution will be in the opposite direction. Hole moves this side and current contribution in same direction, but they are additive, right? So the total current you can write as J. It will be Jn plus Jp. So I'll just write this is whole current density, right? So this is equals to Q n mu n E plus QP mu P into E. Or you can take common, right? Here this electric field. So it is Q n mu n. Okay, Q also can be taken outside. Mu P into E. Now I purposely didn't take. So this parameter or this term is known as the conductivity of the material. So sigma is called conductivity. So effectively we are getting Z equals to sigma into E, right? Where sigma is equals to Q into N mu N plus P mu P, right? It's the conductivity. And similar way you can calculate the resistivity. Anyone? Resistivity is equals to how this conductivity and resistivity are related.
Rho is equal to 1 by sigma.
Exactly. So it's 1 by sigma. So 1 over Q n mu n plus P mu P. Right. So finally, the conductivity of the semiconductor, if you calculate, so for N-type semiconductor, this is in general we did, right? But for N-type semiconductor, the concentration of electrons are much greater than holes, right? So in this case, the resistivity of N-type material, that is, will be just 1 over Q N mu1. So you can neglect this term, right? Because P is much lower. And similar way for P-type semiconductor, this P, the concentration of hole is much greater than electron. Best way to relate with conductivity, then it's easy to follow up, right? So sigma n is just q n mu n, and sigma p is equals to q p mu p, and they are opposite, but here the correlation can better explain. So the sigma n, the conductivity for n-type semiconductor, q is constant, so it depends on the carrier concentration and the mobility, right? Not only single parameter. So some material sometime we'll see the mobility is high, but still the conductivity is low because the lower carrier concentration. So we need to see that. So it depends on basically two parameters, right? Carrier concentration and mobility. And mobility, again, it depends on electric field, temperature, right? So we now understood the drift phenomenon in semiconductor, right? So next is diffusion, right? So this is another way of conduction mechanism in diffusion. So anyone, when do you see diffusion in carriers, or for that matter any material, any substance or any situation? When does it take place, this diffusion phenomenon?
So diffusion take place when there is difference in the concentration of the substance.
Exactly. So whenever there is a concentration difference, or better way of say concentration gradient, then this diffusion phenomenon takes place, and the direction is, yes, higher concentration to lower concentration. So in semiconductor, sometime you will see when you create, let's say, a junction between P and N, because N side we have more number of electrons and P side more number of holes, right? So there is a concentration difference, and in that situation the carriers, they diffuse, right? Now to quantify this mathematically, or write it down in an equation and find out, so there are certain formulas or relations like Einstein relations, right? So we'll just derive those formulas. So the basic is there has to be concentration gradient, right? So the diffusion current density, I'll straightway go there. Diffusion current density, that is, so Jn is to Q into dn into dn dx, right? So in this expression, the dn is called diffusion coefficient or diffusivity, right? Diffusion coefficient, or we call it also diffusivity. Okay, and dn dx is again concentration gradient, right? So dn, we learned, it's a concentration of charge carrier, in this case electron, and dn dx is of course the gradient, right? So it's concentration, and the diffusion coefficient, this dn, is related to the thermal velocity. It's Vth into L. So we know the Vth is average thermal velocity, right? And L is diffusion length. Now you can see that diffusion current is proportional to the special derivative of electron density, right? So Jn, right? And then from equipartition theorem for one-dimensional case, if you consider the electron is moving just only one direction, so in that case, we know from equipartition theorem of energy that the kinetic energy, that is half mn Vth square, equals to half kT, right? Or we can write it as Vth square equals to kT by mn. We defined already, right? Mn is the effective mass of electrons, and we are considering here just one dimensional, okay? One dimension, 1D. So in this case, if you put these values here, dn, so let's name it equation 1. So we are continuing from equation 1 here. Dn equals to Vth into L, right? So it's equals to Vth, and the diffusion length is nothing but again velocity into diffusion time, right? Tau c. So it's equals to Vth square into tau c. And this tau c value we previously we defined, right? Tau c is equals to Qn Mn by Q. So if you put all these values now, so Vth square is equals to from equation 2, so it is kT by Mn. So we are writing dn equals to, so this Vth, we are taking help from equation 2, and tau c we are taking it from here. So Mn by Q, right? So this Mn will cancel. So we'll just get kT by Q into mu n, right? This is dn. This relation is popularly known as Einstein relation, right? Einstein relation. I hope you studied this. Yes, Sairam.
Sir, we have VTH square now, sir. Then it should be KT by Mn square.
No, Vth square equals to kT by Mn.
Yes, yes, sir. Yes.
Yeah. So yeah, so this is for the holes, right? So diffusion coefficient or diffusivity is proportional to mobility, basically. So this is how the importance of this equation. And similar case for holes also we can write it off, right? That dp or diffusivity of holes is equals to kT by Q into mu p. So both this equation, let's write it off, equation 4 and 5. So this 4 and 5 both are called Einstein relation, both of them. Okay, and from here we will calculate in the next class. So already time is at the end. Next class we will derive the total current. So Total current in a semiconductor, if both the phenomenon present, in general both will be present. Sometime drift will be more, diffusion contribution will be less. So depending on the situation we will derive, but the total current is again equal to drift plus diffusion, right? So we'll do that final current equation, or total current in a semiconductor. So we'll derive it in the next class. Any doubts from this session? Stop.